Namaskar everyone. I am Sugyani and I will be your host today. I hope and wish everyone is in good health. I welcome you all to this lecture titled Recent Scenario and Developments in Quantum Computing. Up until now, you learned hands-on basics on quantum computing under the guidance of our mentors and hope everyone utilized this to the best of their abilities. Today's lecture will be given by Dr. Gururaja T.S. He is a physics graduate from Bishop Heber College, Tiruchirappalli. He is currently doing his PhD in quantum cryptography and has a strong background in IBM Qiskit quantum simulations, design and implementation of quantum random number generation, quantum encryption algorithm and quantum key distribution, quantum secure communication through quantum channels, quantum attacks and quantum error corrections, multi-factor authentication for secure corrections, and quantum photonics. Now, I would like to welcome Dr. Gururaja to commence the talk. The space is all yours, sir.
Yes, ma'am. Thank you for your nice introduction. My screen is visible.
Yes, sir.
Yes, sir, it is visible.
Yes. Today we are going to see about what are the foundation concepts of IBM quantum computing and how we are going to implement that basic concepts, basic quantum concepts in IBM Qiskit platform. First, we need to see about what is meant by qubit actually, and what are the properties needed for developing a quantum computing, and how the quantum gates or manipulate the quantum states, how we are going to make a quantum circuits, and how the algorithm we are going to design, how the classical algorithm converted into the quantum algorithm through the bits to qubits, how the bit can be encoded as a qubit. These things we are going to see now, and what are the benchmarks needed for real quantum hardwares that is called as a quantum computers. What are the quantum computers are available? How that quantum computers are going to evolve in the journey of different superconducting qubits, how the every qubit's working on, and error corrections also, and quantum program. What are the quantum programming platforms available to do the maximize of your research? Then finally, what we do in our Sastra University. These things I'm going to tell today's lecture. One minute. Okay, my slide is visible, right? Okay, bit is nothing but 0 and 1 is a bit. So the superposition of the bit is nothing but 0 or 1. The qubit is nothing but 0 and 1. There is a difference here. 0 or 1 only in classical computing. In quantum computing, it is a represent as a qubit. It is a 0 and 1. Simultaneously, it will be verified 0 as well as 1. Here is 1. If I verify the bits, all the data has been stored in the form of digital only. That digital is nothing but in the form of zeros and one only. Any form of information, if you have any sound waves or data in the form of image, all are encoded in the form of bits only. That bit in the form of classical. Here, what we do in a quantum, that is a Hilbert space is that. The Hilbert space is nothing but a vector space. In that vector space, all are encoded. 0 is encoded as a ket 0. 1 is encoded as a ket 1. Like that, all will be represented in the form of qubit state only. The bit is nothing but the smallest information. The qubit is nothing but the smallest information used to represent in a quantum computers. And the values here represent zeros and one. It can be 0 and 1 at same time. It will be verified both 0 and 1 simultaneously, so that only we are able to do the parallel processing here. In classical computing, parallel processing is not at all possible. In quantum, there is a possibility in the parallel processing. We can do the processing everywhere. For example, in one computer, we can do the computation. After that, we can change it to the another classical computer to work on simultaneously. It will be verify all the terms. In normal computer, it will be checked only one time, but in quantum computer, it verify a multiple time. It will be easily processing. The processing speed is also high in quantum computer. Normal classical computer, there is a flip head or tail. Here, whenever if you are spinning state, that the if you toss a coin, the coin in the air, it is a superposition. That is a quantum bit. Here, whenever it is a zero, head means zero, tail means one. In the spinning of air, in air state only, it called as a superposition state. Whatever zero or head or tail, we didn't know about that. In classical, we know about head or tail. Any one possibility, the probability of anything that is one in classical, in quantum, that is a probabilistic in nature. Here, we use to represent the classical information uses electrical signals. Here, we are represent electrons or photons or atoms. The electrical signals, zeros and one, sent to the pulse beam. When the pulse is high, it is a one. Pulse is not there, it will be zero. Here, the electrons, the ground state and excited state will be there. The photons, whenever the photon is enter, detect or not detect, it will be coming under a zero or 1. Get 0 and get 1 is nothing but an excited state or ground state. That is the atom. These are all that. We need to represent the physical information. The physical information of the state can be represented as a qubit. What the major thing in quantum means, in classical, you can able to copy the bits. You can able to information can be able to copy in your classical information. In quantum information, you are not able to copy your information. That is ensured by the principle of no cloning theorem. Any quantum information is not at all able to copy. Copying is not at all possible. Qubit is not at all able to copy. That principle highlight in the quantum mechanics principle. So that only our quantum computing is secure enough so that the QKD is on. So no cloning theorem is the high advantage for the quantum key distribution protocols. Anyway, we are working on high algorithm, high quantum computation. We need to know about what are the basic concept behind it, how the properties are working. Then only we can go for the designing a new algorithm, designing anything. It can be processed. Computation, the process of one state at a time in classical, but the another state, for example, multiple state we can work. Multi-qubit possible, multi-state we can go. For example, in Bloch sphere, you can represent 0 and 1 only in classical computer. In quantum Q sphere and Bloch sphere, you can work on complex algorithm, complex informations also. Only in Fourier transform, you can send the signals only. Here we can use the complex Fourier transform and fractional Fourier transform also currently we are working on. How the fractional data can be transferred to the one place to other. Like that also we can do in quantum. In error sensitivity is less here in classical, but in the limitation here only is the error. The quantum computers are prone to errors now, so that the error corrections are majorly work on this scenario. Currently, the error correction is the higher thing. Check what are the qubit representations are there in that electrons. For example, in nucleus, there is an electron state will be there. The state is get 0 and get 1. It is possible. The trapped ion, the qubits or quantum dots are all possible. The photons is all. These are all the quantum computers currently available. Superconducting qubits. IBM is currently working under the IBM superconducting qubits. Photons, if you see, means the Quandela hub and Strawberry Fields Xanadu, that these two platforms is working on photons. We can send the information as a photons here. E is energy is equal to h nu. H is nothing but a Planck constant. Nu is nothing but an instant frequency of photon. Photon is nothing but a light particles. Light particles we will send through the information here. The photonic quantum computer. Trapped ion quantum computer is also available. Whenever the electrons is come, we can trap that information as the quantum state. Here the quantum dots also available. These are all the quantum representations are currently available. What we do in a kit 0 is nothing but 1 0. The 0 in the form of 100%. The 100% of 0 is here, so that it is a 1. Here the occurrence of 0 is 100%. The 1 is 0%. So that here 1 0. Ket 1 is nothing but 0 1. This is a basic ket 0 and bra 0. This ket and bra is nothing but a Dirac notation. That Dirac notation is a vector notation. We any form in quantum we need to represent in a vector form. Superposition, it rely on both the zeros and 1. The superposition breaks creates the randomness. Any quantum random numbers need a superposition state. Hadamard gate produces a superposition state. How it produces kit 0 is represented as a kit plus state, and kit 1 is nothing but converted into a kit minus state. This both states conversion happened during the principles of using the principle of superposition. Superposition is nothing but kit 0 and 1. Entanglement, anyway you are representing a 2-qubit system. 1 qubit, if you change anything, automatically it will change another qubit. So that if you want to send one data in the form of entanglement, through if you are changing here, automatically changing the other state in other place. So you are in Nepal, I am in Tiruchi, Tamil Nadu. If you are sending any data to me, if you alter anything in your place, automatically change other state to me. If you have 1, if you convert it into a 0, I will get 1. So the information changing has also possible through the entanglement. So the entanglement QKD is also available currently. Anyway, that we working qubit is not able to copy, that ensures by the no cloning theorem. In coherence we need to maintain, then only the superposition is possible. So all the quantum computers are rely on coherence. Coherence means, what coherence actually means, we need to maintain the superposition state. 0 and 1 we need to maintain, then only we are able to generate randomness, and all the quantum information has been possible. Qubit is a fragile qubit having only the microseconds to work on. After the microsecond, it lost its superposition. So it not behave like a quantum computer. It will be behave like a classical computer only. That microseconds to minutes they are working on. All are working on to enhance the speed of the coherence level. Speed of the coherence level need to maintain. Whenever the coherence is maintained, then only we can able to see the spinning coin in the air. Like that, superposition is possible. If you measure that state, it will be decoherence. You will not get the same state. If you measure the device, you will not get the same outcome. It will be collapsed into the single state. That will be. And major property is interference. Any quantum particle, it behave like a multiple superposition state only. It can be used as a particle as well as wave. When it is these are all represent as a probability amplitude. When it is added up, more likely. If it is not cancelled out, less likely. For example, what I'm going to say about Young's double slit experiment, whenever the condition is a bright, it will be 1. It is a dark, it will be 0. Like that, the double slit experiment only proves that interference concept. Here, what is the quantum interference? Whenever the state is high, that is a maximum probability. The maximum probability, if you get, that is a correct answer. Minimum probability is the wrong answer. You need to show every time you need to identify the maximum probability, because the quantum computer has some errors. So that you need to go with the maximum thing. Quantum algorithms like Gruber's or Shor algorithm used to identify the increasing chance of correct answer using the principle of constructive interference. Reduce the wrong answer by the principle of destructive interference. Whenever the amplification is high, the constructive is a quantum state like a water waves like. Whenever the states is coming, constructive means it add up the value. Whenever it is a district means it cancel out. The bigger amplitude means higher probability. Smaller amplitude means lower probability. They are in sync in higher probability. They are not out of a sync in lower probability. Whenever you measure only you know about what the quantum state is. Any way you are, if you measure, that will be a classical outcome only in final. What are the, how the coherence is maintained in quantum computer? Superconducting, IBM has a superconducting qubits that you can able to maintain the 100 few second, 100 microsecond to few millisecond only, the coherent state will be maintained. After that, it will not use that coherence time. Trapped ion 1 second only, but it has lower qubit level. You see the superconducting qubits only have a 133, 156 have qubits length, but trapped ion qubit only the less than 50 only available. NV center diamond we need to know. So that room temperature also we can maintain the qubits. But the NV center has the disadvantages of room temperature, noise, and other thing. Photonic qubit, photonic quantum computer have a photon loss is also happen. The whenever the optical loss will be happen, it also maintain the microsecond to milliseconds. What we need actually if you want to work on superconducting qubits, you need to have a cryogenic cooling. Whatever we are working in IBM quantum simulator is IBM quantum computer means we are sending the information as a quantum. First we need to design our quantum state as per quantum gate. After that, whenever we measure and send that job to the real quantum hardware through the microwave pulse, all our quantum information sent through the microwave pulse. That pulse has been changed into the quantum computer. The computer made the performance using the low temperature millikelvin cryo-electronics device. That cryo-electronics send the again signal to us. We will convert into the classical bits and see the how the outcome is coming by the histogram level probability. The material purification is also needed. 3D cavity shielding and error correction codes also needed to maintain the high coherence state. We need to see here. You can see the how long the quantum state can be open. For example, these are all the environmental distribution. Environmental disturbance is high means it will not lie. How the superposition occur, I will show the real implementation. Case 0 is whenever you switch on the computer, it will be automatically like a 0 only. Whenever if you add the Hadamard gate here, you will see the both probability here. Whenever if you measure, it will be collapsed into the state vector here. Here you can see the state vector is 1 only. Whenever I measure, I'll start again this implementation 1 minute. This implementation you can see get 0. Whenever if I added the Hadamard gate, it will be produce both 0 and 1. It is a superposition state. If I add the measurement gate, it will be collapsed into a single state. 0 can be converted into a 1 like that. Here, the one state only possible. This is the IBM quantum platform, IBM quantum composer. Here you can work on. This Q0 is nothing but a quantum register. C1 is nothing but a classical register. Equal number of quantum register and classical register needed whenever you are working in quantum composer or quantum computing, quantum gate and circuit formation. You need to remind in mind equal number of quantum register and classical register needed. Whenever you are working on any quantum gates, that will be finally stored into a classical outcome. That classical outcome can be stored in the classical register here. This this is shown here. That is a phase disk. Phase disk means how the phase occurrence. The quantum has not a 0 and 1, it has a phase value also. The phase value here it will be shown. That phase value maximum 0 or 1 like that it will be shown. This is a open quantum code. This is quantum assembly language program. Here you can change into the quantum assembly into the Qiskit code. That Qiskit code is nothing but a Jupyter notebook code only. Normally you are doing like C program, C++ program, Python program. Like that Python program, you can, these all are run in the Python program only. Whatever you add that gate, respective code will be generated here. You can copy that code and work on Jupyter notebook or Python based simulation also. Whenever we are here, you can see the Gates. What are the gates currently available? Hutch gate is a single qubit gate. NOT gate. This is C NOT gate. C NOT gate is controlled NOT gate. Whenever the control state is 1, then only it will be activated. That will be shown next demo. Here, these are all the quantum gates. What here, whenever you click the gate, you can see the gate details also here. Adamant gate only produces a random number. How the random numbers here occurrence? For example, I need to initialize first a quantum register in the form of 24 quantum register. Like that, I need to add the classical register also 24. Whenever the Hadamard occurrence produces an unpredictability will be there. Superposition will be there. Whenever if you measure that one, whenever measure only you know about 0 is there or not 1 is there, you will be no. After that only you know. Whenever after your measurement only you are able to know about what the outcome is. So that if we measure all the quantum register, we will not get the same outcome. The outcome will be a low or high. That can be varied. So that Hadamard is used as the basic randomness. Whenever if you use Hadamard with the other gate, it will produce a complex randomness. Like that, you can go on to generate a different quantum random number. Here, I need to show about the C naught gate. How the C naught gate links the entanglement. Whenever if first state is 0, means it will not work. Whenever the first state is get 1, I initialize the 0 into the 1, it will be changed. I measure first time it will not change. After I measure, it will be changed into the 1 1. Finally, the probability here it will be varied. Again, I will show. Whenever I added the normal C naught, it will not work because both are 0. First one 0, second one 1. So it shows the 1 is 0. You need to read the quantum gate in the form of MSB to LSB, maximum bit to lowest bit. Here you can read 1 1 is the outcome. First state is 1. Second state is controlled by the first state. Whenever the first qubit is 1 means it will be controlled by this controlled gate. Here it is 1, it will be flipped into here also 1. So the 1 1 is possible using the this gate. This gate is nothing but a C NOT gate, controlled NOT gate. First gate is 1, automatically flipped to the other gate is also 1. 1 1 it is possible here. You can read like this only. Back to front. MSB to LSB 1 1. Here you can see C naught 0 0 1. First it will be 0 0. After that 0 and 1. It comes at 0 and 1. Finally, it will be added into the 1 0 1. Second state is 0 only. It will be control gate. Action of the control gate. It will be converted into a 1 1 here. If you measure means the probability of occurrence change. Finally, only you will get the results in probability. You need to see the outcomes in probability, not in a state vector. Before, whenever if you not measure the quantum state, you will see the state vector probability. Measurement. How the measurement occurs? Hadamard. I apply the Hadamard in first qubit, first quantum register, and second qubit also I apply the Hadamard gate. You can see that the state vector is also 0 0 0 1 1 0 1. Measure probability also 0 0 1 0 0 1 1 0. Whenever I measure the 2 qubit collapsed here, you can see after I measure all are collapsed into the single state here, but the probability of occurrence is high. Here you can see the maximum probability of 0 1 is 24%. Another is like that, it will be vary. Here you can see the randomness. The histogram changes. For example, 20% 0 0 will be there. 0 0 0 1 0 1 0 1, and like that the random occurrence will be there using the Hadamard gate. Here you can see that quantum register Q2 2 qubit will be there. C register, classical register also same. After that I apply the Hutch gate in 0 and Hutch gate in 1 state. Whenever I measure, I need to measure all the register. Quantum register will be stored into the classical register. So the quantum outcomes will be stored in the classical register. Finally, you need to run this 2 qubit in real quantum hardware. You need to sign in the platform. After that, you need to click here, setup and run. If you click the setup and run, it will be open real quantum hardware. Whatever the shorts is nothing but how many times your quantum circuit going to run in real quantum hardware. How many times your quantum circuit going to run in real quantum hardware, that can be decided using the shorts. That shorts you need to enter. Finally, you need to run any one of the quantum computer. IBM has a quantum computer. It is an open source platform, free only. You can access for 10 minutes per month. You can able to work on real IBM composer, as well as you can download your IBM quantum quiz kit using your Jupyter notebook. Also, you can manually, locally install that things also. What is quantum gate? Quantum gate is action of the qubit. What the quantum gate will be working on? Rotate and mix. Rotate, compute, quantum computing. The simple form of quantum computing, rotate the states. For example, you need to have the Bloch sphere. That Bloch sphere is nothing but cos of 0 plus e power I5 sine theta of K1. That is the unitary operation. That unitary operation, you are going to change any quantum gate in the form of unitary operation only. Unitary operation is nothing but U is nothing but a gate. One quantum gate is in the form of complex form. That quantum matrix has been encoded in the form of qubit. That qubit, you can make the rotation and mix the state and entangle the two states to make a powerful new states. You need to generate new quantum state. How I make that quantum gate only? How the quantum gate is working on? The gate, all the gates are working in the form of unitary gates. You need first, these are all working in the principle of superposition. Flip the qubit. If you want to flip the qubit, whenever you have a NOT gate, apply the NOT gate, 0 will be flipped into 1, like same NOT gate. That here also available, that is a X gate. If you want to change the phase, you need to add the rotation gate, X gate, or X gate, or Y gate, rotation about the X axis, rotation about the Y axis, like that the gate will be there. All are stimulated using the form of Bloch sphere only. Whenever you rotate the Bloch sphere thing, you can design your own quantum gate. Custom gate also you can create using the IBM composer. If you want to add the two quantum gates in the form of single quantum gate, that is also possible in IBM composer. You need to crop that two gate in the form of adding these things. Entangle 2 qubit. You need to entangle 2 qubit. You need to have a C0 gate. That C0 gate, whenever the first qubit is 1, it will be flipped in the another gate. Like that, it's go on. Here you can see the circuit. Quantum gate is manipulating the quantum states. Quantum circuit is connecting the gates. Circuit is connecting. Normal circuit is connecting the gate, right? Like that, the circuit is connecting the gate. The algorithm specifically work on the what the instruction we are giving, how to solve the problem. All the problems solved by the class quantum circuits only. You need to design a quantum circuit. Before you going to know about the quantum circuit, that you need to know about what is gate. If you want to know about the quantum gate, you need to study about what are the matrix back on that. First, you need to work on theoretical calculation. After that, you need to come for the quantum gate selection and design a quantum circuits. After that, make one algorithm. First, start with the basics of QFT, quantum Fourier transform algorithm, to solve some specific problems. After that, you can move with the other like Grover's or Diaz-Jasa, Benzi-Vignani. Like that, you can go on different algorithms. What is actually in classical gates, classical NOT gate, and these are all the classical and quantum gate will be also there. What are the operation in normal gate will be working on? These are all the classical gates. AND gate is nothing but when the output is one, the both inputs are one, then only the output is one. Like that, the quantum equivalent gate is Toffoli gate. OR gate is nothing but output is one if at least any one of the input is one. That is a Toffoli plus NOT gate. You need to add. What are these gate? You need to know about adamant gate produces a superposition. S gate and T gate creates a phase of the qubit, changes the phase of the qubit. Swap gate changes the position of the qubit. For example, you have a two data. I need to transfer first data to the first qubit. I need to use the swap gate. Rotation gate. You need to rotate the qubit state in the form of, for example, I need to add my 125 in the form of representation of Rx. I entangling layer that, for example, you need to represent the image in the form of FRQI, flexible rotation qubits. That FRQI is the image representation. That FRQI is encoded using the rotation gates. Or first you need to know about what are the quantum gates are available. One single qubit gate, two qubit gate and multi-qubit gate. Like that you need to study. First, what are the single qubit gate? H gate and S gate is a single P gate. Like that, these are all working on the single qubit gate. Toffoli gate is a control not gate. That is a Toffoli gate. Control gate means what? When the control state is zero, no, it will be same only. When the control gate is one, it will be flipped into other state. Like that, it's go on. How to do the classical to the quantum transform, how we change the classical to quantum, bit to qubit. Normally, basic state is nothing but 0 and 1. That is a computational basis. 0 1, that is a computational basis. Normal classical computer will be what? All images, all data in the form of classical only. We need to convert in the form of quantum. That quantum we need to convert means we need to use our matrix representation. Ket 0 is nothing but we already know about 1 0, and Ket 1 is nothing but 0 and 1. 0 time. Whenever the 0 here, it is 0 means what? The 0 state will be 0. The 1 state will be 1. When the 0 state is 1 means 100 times. The maximum probability of the state is 1 here. Here that 100 times shows here. 0, Ket 0 is nothing but 1 0. Ket 1 is 0. This is the computational basis. Qubit we represent as a psi is the wave function, is nothing but a both of Ket 0 and Ket 1. Alpha and beta is a complex numbers. It will be work on the basis of magnitude and the phase. It will be 1 only. Anyway, our total probability must be in 1 only, 100% only. First, we need to choose a physical system. What do you mean by physical system? We need to work on superconducting qubits, photonic qubits, trapped ion qubits, and D-wave quantum annealing and trapped ion topological qubits. These are all the 5 quantum rich quantum computers also available. So that you need to select one quantum computers. If you want to work in superconducting, you need to fix on superconducting. And if you want to work on photonics, you need to select that physical system first. After that, you need to identify what qubit you are working on. That thing you need to identify. In superconducting qubits only have the large qubit. So that it called as a NISQ era, a noisy intermediate scale of quantum computer. In photonic qubit, what is the advantage? Now I'm working on why I'm working on photonic quantum computer. It will be work on modes. Photons is work on two modes. In normal two modes, I'm able to generate a 1 crore quantum random number data. But in IBM superconducting qubits, the equal number of quantum register and the classical register needed. The quantum register quantum qubits into shots. For example, 1 qubit I'm working, 1 shot means I get a 1 into 1, 1. If I'm working 1 qubit into 1 lakh shots, how many shots maximum possible means 50,000 on 90,000 maximum possible. I need to run my same circuit maximum 50,000 I run. Actually, it will be work only for 80 to 90,000 only. If 1 lakh only, 1 lakh bits, 1 qubit is possible. But if you want to work with more data, you need more data for random number generation or anything. You need to work on high data. You need a more qubit. That more qubit needed in IBM compound. IBM superconducting qubit. If you want to work with photons means it will be work on lower qubit, lower scalability will be there, modular will be there, so that you can work on photonic quantum hardware also. But here the error correction will be there in IBM quantum computer. That photon loss is also there. Anyway, if you go any physical system, there is a one advantage as well as one disadvantage will be there. You need to identify the physical object. Better you can go with superconducting qubits of IBM. IBM having an open source, so that you can go with the maximum time of practice also. In classical computer, 0 and only, you need to change the qubits in the form of spin or polarization. Spin is nothing but electron. When the electrons have a two spins, half integral spins. One is a 0, another one is a 1. That to have spin up, spin down. is possible in electron. Photon state polarization. What are the polarizations are? Horizontal polarization, vertical polarization, diagonal polarization, half diagonal polarization. These four polarization needed for QKD. If you are working on quantum key distribution, you are going to encode your qubits in the form of polarization states. That polarization state is nothing but K plus, K minus. That is the both two states are available, K plus, K minus, diagonal, anti-diagonal, and the two states. And these are the current direction we are working on the current superconducting loops only. Finally, initialize the classical state. The classical condition you need to work on get zero. Usually we start zero only. If you are working on your one normal computer, it will be booted up. That booting is nothing but a get zero. That get zero is a horizontal polarization. Apply that into the quantum operation like superposition. Anyway, if you want to start in a quantum computing, you need to know about how the Hadamard gate is working, how the Hadamard gate produces a superposition, you need to know. The Hadamard gate, when Hadamard gate is a major thing for all this quantum superposition. Hadamard gate basically into the state, normal state in the form of quantum superposition state can be possible. It will be partially zero, 50% zero, 50% one at same time that produce using the Hadamard gate. That is a quantum operation. Here you can see the operation in the form of rotation also. I am not only rely on Hadamard gate. Because why I am not really relying on Hadamard gate means Hadamard gate is a single qubit gate. Single qubit gate is not known by the since some of the gates are not known by the real quantum hardware. Real quantum hardware know only the some basic Clifford gates only. Some gates like OR is a gate, I gate, like that gate only know about the Hadamard transpilers. So whatever the gate we are implementing in normal, that will be transformed into the transpilation process. The transpilation process is converted our class quantum gates in the form of the other thing like quantum gates has been converted into the transpiler. The transpiler modify our gate to other equivalent gate that will be run in the real quantum hardware. We need to maintain the coherence, how that mixed state can be product in the environment. If it is a isolation or low temperature, error control has been working on real quantum hardware. If you need to operate any quantum gate, X gate flips zeros into one. Z gate changes the phase. C naught gate entangle the two qubit. You need to identify that two qubit has been entangled, merged to the single state. Like that, these operations compute the superposition and processing many possibilities like that. Qubit collapse either 0 or 1. The probability of getting 0 and 1 depends upon the rotation. How you rotate that state, that will be identified here. Hadamard with the get 0, it will be produced as get 0, 1 by root 2. The two possibility, 50% it will be 0, 50% it will be 1. Here, this is a Hadamard gate Hadamard gate matrix 1 by root 2, 1, 1, 1 minus. How it is occur? How this can be represented as a get plus? The input state is 0, get 0, right? 1, 0. It will be multiplied with this Hadamard matrix 1, 1, 1 minus 1 with 1, 0. I need to operate the tensor product. First row, first column. 1 into 1, 1. 1 into 1, 1. 1 into 0, 0. Minus 1 into 0, 0. So that 1 by root 2, 1, 1. This is a get plus state. If you operate with the 0, 1, what it comes, you need to know. Here, you need to change with, if it is a get one state, you need to work on 0, 1. Here you need to change 0, 1. How it will be 1? 1 in the form of 0. 1 into 0 plus, like that you need to work on this matrix. This is a tensor product. Here you need to multiply first row, first column, like that matrix multiplication. Then only you can perform the qubit manipulation also. You need, anyway, your quantum circuit start with get 0 only. You need to work on get 1. You need to add the C naught gate. First not gate you need to add. then not gate flips into 0 into 1. Anyway, your circuit start with 0, so that you want to stay work on 1, you need to add not gate. Finally, you will get that. Finally, if you work on 0, 1 and 1 and 0, you will get 1 by root 2 of gate 0 and gate 1. That gate 1 by root 2 of 1, 1 is nothing but 1 by root 2. 1 is nothing but 0 is also how many percent? Here it is nothing but 1 means 1, 0 plus 0, 1. That is nothing but get 0 and get 1. Here 0 is the 1 by root 2 whole square. 1 by root 2 is half. 1 by root in the form of root and square will be cancelled, and 1 by 2 will be there. The 50% possibility of measuring the 0 will be half. 50% will be 1. So equal likely 0 and 1. If you generate any random number, if you split into 2, how many 0, how many mean, it will be equally splitted into a how many 0 and how many 1. That equal number of probability will equal mix will be there in get 0 and get 1. 50% of getting 0 and 50% of getting 1, like head or tail. Until measured, you know, if you spin a coin, the coin will be in the superposition state in high R. If you tap that coin, you will know about what it is 0 or 1. Whenever you measure, you will toss multiple times, you will know about what is 0, what is 1, like that you will be able to identify. Get 1 is nothing but 0, 1. Here, the mix of interference is there. We need to, whenever the simple things, we need to add some quantum technical terms like relative phase. What do you mean by relative phase? Change the value plus into minus, that vary the state. Plus to minus means relative phase, like interferences happened, like that we are adding the small technical term. Hadamard gate creates superposition, makes a spin, qubit spin. How it spins, you can see. I add the gate plus state, add H. Here you can see the color change. What the color change actually means, here you see the phase disk here. That phase disk pi by 2, 0, 3 by 2. These are all the phase disk. Here the color will be there. Whenever it is 0, it is a blue color. Whenever it is a 90-degree, that pi by 2 is a 90-degree. When pi is a 180-degree, that pi 180-degree, it shows the what color? Red color. Here you can see I added the one, apply the Hadamard. I'll change, it will be change the color. You can see the one color into a red, blue color into a red, blue color into a red here. This color change happened the phase manipulation. Blot sphere. Why we need the blot sphere means how the rotation happens. 0 into 1, how the state changes, that can be easily visualized. You can able to visualize your qubit state. You can understand what is the superposition, how the phase can be changed, how the rotation can be changed into the quantum gate. That also you need to work on only the blot sphere. Blot sphere is the basic of quantum representation, qubit representation. You need to predict the measurement on how the measurement outcome will be there. That is a Z is nothing but a measurement basis. How to study the noises, how to debug the quantum circuit, that will be identified this blot sphere. How the quantum algorithm is working, that quantum algorithm is basic of set of instructions we need to give the quantum computer in the form of qubits. Classical computer is working on the normal computation. You need to work on quantum computer. You need to convert your classical outcomes into the qubits in the form of quantum gate by the applying of some instructions. Quantum algorithms work on zeros and ones only by applying these principles like superposition, entanglement, interference, to process it into the parallel to enable the faster computation. Like classical computers not able to solve the complex problem, like you have a 10 numbers 5875 like 9834 into 789312920, like that. What is the factor? You need not know about. Classical computer takes a longer time to find the factors, but in quantum computer works on the principle of parallel processing to solve that problem, maximize level, to find it in the microsecond level. It will be show the results. So that only our quantum computers are working. Quantum algorithms work on the sequence of quantum gates as well as measurement. Measurement is a main. Whenever anyway you are working on quantum computer, you are not able to see the outcomes in quantum computer. You need to see that outcomes in your computer only. So that you need to measure that quantum gates. Then it will be converted into the quantum states into the classical state. You need to see that classical state after your manipulation and all. Works with the bits zeros and one in classical algorithm. Here we are working in the form of works with the qubits 0 and 1 or both the 0 and 1. Here the classical algorithm we need to know about the deterministic state. Normal classical rand function, Python rand function is a deterministic. Meissner twister only work on the principle of Python rand function. That is a deterministic. If any ML algorithm are also able to understand what is the classical algorithm will work, but in quantum algorithm is not able to know about the any ML algorithm 100%. 20%, 10% is possible in ML algorithm also, but 100% not at all possible because the outcomes are probabilistic. How I am verifying? I am running my circuit again and again. And that is a restart experiment. I restart my experiment. I get the outcomes. It's not at all same. I want to know about my outcome. One. No, I want to get my outcome again. It is not at all possible. So that I need to store my outcome also same. So we are not able to generate the same random number again because of probabilistic nature, because of uncertainty, Heisenberg uncertainty. These principles are majorly work on the superposition here. How the quantum algorithm work? First, you need to initialize the state. Initializing the state in the form of kid zero not only kid zero. Here, the IBM quantum composer, you have a QC dot initialize. That initialize, you can change that any value. If you want to work on 0.1 to initialize your quantum state, you can initialize. But in classical algorithm will not initialize normally 0 on 1 and 1 by 2 fractional value like that it will not initialize that. Here you can do that initialization. After that you need to apply the superposition. Hadamard gate is a familiar gate to represent the superposition. You need to show your superposition. Without Hadamard gate I am using Rx, Ry, P, these three gates to represent a superposition, or Rx, Ry also you can work on superposition like that. Any rotation gates with the particular phase can be able to create a superposition. That is a novel, not Hadamard. You don't rely on what Hadamard only. You can use Rx or Ry that also make to convert a possible superposition state. After that, you need to make an entanglement. Normal Bell state is nothing but you previously studied about what is the Bell state. Bell state is nothing but H with the C naught. The H with the C naught will be create a Bell states. Bell based entanglement. That entanglement is working on whenever the control operation will be there, the entanglement is possible. Entanglement needed a two qubit. One qubit is there, another qubit will be flipped into the other state. First one is 0, another one is a 1 automatically change. The entanglement has been possible. Interference also matter. When you work on interference is a matter. Why interference is matter? All the things electrons are sent in the form of in the particles of dual nature will be there here. Either it will be a particle or in the form of waves. The wave is high or low, it will be ensured by the interference only. Whenever you measure only, you know about the what the solution is occur. That measurements, whenever you measure only, you know about it. Why use our quantum algorithm? Quantum algorithm can perform the faster task like a classical. Classical is not working on the faster task. In quantum algorithm is faster than the classical. For example, you need to search the large data set one single value. You need to find the hashtag is there. You have a more number of nail. You need to find a one nail in one box. You can easily identify like that. Not large phone number, telephone directory is there. You need to identify one telephone number. You can use quantum algorithm to work faster. Factoring large numbers, stimulating molecules. You can design your own quantum molecules also. Normal molecules can be solved in DFT, DFT, density function theory, that quantum function theory is also working uh, very high speed. Normally, DFT, density function theory, will be work on low level only. If you run one algorithm, it takes 1 day or 2 days. Machine learning algorithm training time is very large. But in classical quantum computer, it will be faster, like a microseconds. Deals Jasa, it introduced the determination function as constant or balance. These are all work on the speed up of classical exponential over the classical and the unsorted database. You need to find any data, any algorithm. For example, Groovers, we are working for a key search algorithm. Classical, all quantum secure thing rely on keys. Key is the major thing that we need to add. For example, if you want to generate OTP or any CAPTCHA, any security algorithm relies on key random number. That random key has been attacked by the Groover. Groover is an algorithm to attack, search the key in the database. It will be working on the quadratic speed of root 10. So SHOR algorithms also break the RSA crypto system. It will be factor in many things. Many classical algorithms are break by the Shor's algorithm. Peter Shor's is break the factorization problem to break the RSA crypto system and AES crypto systems also. QFT, quantum Fourier transform, is a many core algorithm. Anything you need to convert the quantum state to the frequency domain. Normal 1 qubit QFT is nothing but Hadamard gate. Hadamard gate, what it will be convert? Gate 0 into the gate plus state. Gate 1 is the gate minus state. That two state computational basis to the Fourier basis that can be worked on the quantum Fourier transform. This is also we are majorly working. And quantum phase estimation, you need to find the eigenvalues of the eigenvalue and eigenvector will be there to stimulate the phase estimate. What are the phase? Actually, phase kickback. These are all algorithm work on the purpose to maintain the crucial simulations like molecular design and drug design. New drug design, you can work on QPE as well as VQE, variational quantum eigensolver, to find the lowest energy state of the hydrogen molecule or any molecule. Here, this can be worked on the hybrid quantum classical work. IBM introduced the benchmark to the quantum computer, layer fidelity. What do you mean by layer? H gate, you add H gate, CNOT gate, or X gate, like that. Whenever you add a mini gate, that is nothing but a layer. One layer is first state, another layer is another gate. Like that, it will be all the information revealing about the individual qubits only. Individual qubit only know about what is the states are. And the quantum processing speed is high in IBM quantum computers. CLOPS. What do you mean by clocks? Means circuit per second. How the circuit is working fastly in the form of quantum volume. The quantum volume is also high in superconducting qubits. Circuit depth, the number of parallel gate execution step is determined by the circuit depth. The processing unit run before the qubits decohere. The decoherence will happen this time. Know about this real quantum hardware, so that the processing unit can be run within this decoherence period. Within this coherence period, it will be working. Whenever it is decoherence, it will not going to that time. The circuit depth we need to know. We need to know about what our circuit depth is, how it going to, how the complex circuit can be run our computer. These are all the general purpose quantum programming platform that you can able to work on. First, IBM QuizKit, it's an open Python library based. You can able to build your quantum circuits and running into the real quantum IBM cloud platform. You can use this as an educational and research algorithm development. And Google has also a quantum computer, that is a Google Circ based quantum computer. These are also working in the form of Python based. Here we can use the gate level simulation. Microsoft Q. Here we are not using the Microsoft Q and Azure because the high level quantum, this is the high level quantum programming, but it will be work only for the hybrid classical applications. If you're working on hybrid as well as classical plus quantum, means you can use Microsoft. Amazon Web Series, it is a working on real quantum hardware. If you want to work not only a simulator, industrial and academic based, very big hardware simulation, you can work on IBM bracket. This is all cost based. Xanadu-penilin, here you can Xanadu-penilin supports a type. We mainly work for the machine learning algorithm and optimization problem and quantum chemistry problem. You can work with Xanadu penilin. Penilin have another one is nothing but strawberry fields. That strawberry fields majorly work for a quantum photonic programming. Q-tip is also quantum photonic problem, and Q-tip you can work on open quantum systems like theoretical. For example, if you want to solve some theoretical problem, you can use the Q-tip Python based quantum toolbox. And project Q is ETH Zurich. They are designed. This is also design how to design the quantum circuit and compiler based research. You can work on this. May anyway, the open source and highly used quantum platform is you can use IBM Qiskit. So many learning platform available. So many are know about that IBM Qiskit, so that you can many resources are available. Qiskit Nature, here you can work for quantum simulation and quantum chemistry. Qiskit Nature is available. You want to molecular design and you want to make a structure in the form of chemistry and material, you can use the Nature. Qiskit Nature, you need to create your own quantum hardware also. You are able to design your own quantum computer, superconducting quantum computer using the Qiskit Nature. Open Fermion, this also convert chemistry problem in the form of circuits. Penilin Q Chem, that is also working on machine learning algorithm. ORCA quantum chemistry, this is also machine learning task, and NAM5. These are all the normal machine learning with molecule simulation chemistry. And cryptography, what we are working on, simulacron and QNetSim, that is a simulator. Cryptographical protocol like BB84, E91. These are the protocols able to simulate much better. QKD NetSim, network-based QKD performance, that is also based on Chinese Academy of Science. In any research, in research area, Chinese Academy of Science is a top level network research. Lip Quantum, it is an open source also. Here you can simulate a QKD in the form of visualization and testing your thing. And NIST Open Quantum Safe. Yeah, NIST is the post-quantum algorithm to secure our ML. If quantum computer comes, how our algorithm can be secure? That can be work on the MLChem algorithm and dilithium based digital signature hardware program also we are working. That is a post quantum cryptography. Machine learning, you can work on Penilin and Qiskit machine learning algorithm also you can develop using the quantum neural network and machine learning based tasks. Optimization, if you are working, you need to work on DB. What do you mean by optimization? GPS location will be there. You need to identify one particular location, one particular area. That particular area, you need to identify the smallest path. That path also able to do with the QAOA and QPO problem using the D wave quotient, that annealing based problem. And you can work on that QAOA in the form of NIST also. For example, that Qiskit also you can able to work optimization. And network simulation, NetSquid and Qiskit you can able to work. And if you want to do first of all what is the basic thing and all, you need to rely on IBM Quantum Composer. You need to drag and drop the quantum gates. You can build your own basic quantum simulation using the IBM Quantum Composer. That is a major thing. Block space representation, Qiskit Q-tip is also okay. Indian-based quantum circuits, quantum simulator, QKD set up by CDAC and TIFAR. They are working on secure quantum key distribution simulation only. And boson CQ, they are working on aerospace and material-based Q-Krishi. They are working on SDK. SDK is nothing but software development kit they are making with the form of cloud-based quantum computer. TCS is highly working on optimization and ML stars. What we do in our Shastra Quantum Continuum Group QCG, we are working on quantum random number generation by using the different quantum gates to make quantum true random number, quantum pseudo random number. Pseudo random number is nothing but we need to give the true random number as a seed to generate a quantum pseudo random. That hybrid random, true random plus pseudo random, by the form of same circuit, that is a hybrid quantum random number generation. Finally, that quantum random number we are generate that random number in the form of applications of OTP, secret key generation, encrypt the data, and many things. Hybrid quantum image encryption we are working on. We need to work on both the DNA in the form of quantum. DNA is encoded into the quantum states. Finally, we encrypt the DNA in the form of DNA based computing and quantum based computing. We are hybrid the two into the image encryption and quantum inspired photonic crystal biosensor applications and gas sensing and enhanced quantum image encryption with the blockchain based distributions also. And our system groups also we have what they are doing ionospheric studies with the IIT Tirupati and 6G communication added with the QRNG module in the 6G communication, secure 6G communication, and anti-spoofing also. We are getting the satellite data in our Shastra by using the receiver. That receiver data has been secure by anti-jamming and anti-spoofing mechanism using the QKD protocols. We virtual to communication, that intelligent reflecting surface. These are all work for the Indian armed force we are working on. These are all secured by our quantum hardware. And that drug delivery systems, that long action, we are added a quantum sensor to make the quantum sensing much better. Spray and dye pharmacological studies also we are added the quantum simulation much better using the material synthesis of quantum material. Traditional Indian system medicines also we are preparing in our labs. And AML, that all the AML processing research group, what they are working, input images is converted into the secure quantum image data secure, and that the image can be processed into the multi convolutional network and future extraction and many AI and ML advanced research of tumor classification and identifying the brain tumor and identifying the disease verification, how the survival state can be using the prediction using the Gilo-Cirque network. That deep Q algorithm, deep reinforcement learning also we are proposed for the tumor classifications. Thank you. Here you
Thank you
can.
very much, sir.
Yes, ma'am. This is the IBM
Um,
quantum platform. Users, you can do this way to identify. This is the way you need to open your composer. You can add and delete your quantum register. Superposition already I shown. Whenever you measure, you will get the one state. 2 qubit superposition. You can see all are 25% each only. After measurement, you will get the probabilities are here equal, but in final state measurement is 1 only. But here you can see the probability difference. Whenever you add again, the probability will be change. That creates a randomness, quantum randomness. Now you are going to see about the NOT gate, action of 0 into 1. After I apply the H gate, what it will change? The phase change has been occurred. If you measure, it will be only 0 only. Controlled operation. How the controlled operation? Whenever the first state is 0, 1, 1 only, it will be flip into a 1, 1. Otherwise, it will be 1, 0 like that. I apply the first in the 1, 1. Here you can.
You have forgot to share the screen. You are still on the Microsoft PowerPoint. You have said that.
What?
You have said the Microsoft PowerPoint screen. I think were you
Yes.
trying to show the the using of the computer, the algorithm steps?
Now you are able to visible, right?
Yes, yes.
Didn't know about this also. All are having the IBM ID, right? Or not having.
Yes, yes. We are right.
How to create the ID I am going to show faster. IBM Quantum Platform, login. You need to sign in first to create IBM ID. Go with your password, dot, finally next. You need to get one verification, identification. After identification, you need to create first you don't mention your use your institutional ID. Then only you will get the access of free. Otherwise, you will not get that. Finally, proceed. You will get one password. You need to enter that password, and you need to here you can enter your institution name. Finally, you will get that access. Here, the dashboard in IBM Quantum Learning also there. Whenever you complete any courses in IBM Quantum Learning, you will get the batches. So that you will make a IBM QuizKit advocate also. You are able to develop your skill in the form of QuizKit advocate. So you can able to work on with IBMers, IBM company persons, you can able to work with that. You need to add your quantum circuit name. This is a quantum register. This is a classical register. Phase disks. These are all the quantum gates. Here open quantum codes is also available. This is what this quantum register and probabilities also. You can add and delete your quantum registers. Like that you need to create. Anyway, you are working on quantum computing, you need to prepare unitary state, preparation, state evolution, measurement. These three things will be happening. This is a superposition. I already shared this. See once you can able to know about what is hatch. Whenever I measure, it will be 1 only. Superposition will be collapsed. And this is 2 qubit. I added a hatch. You can see that probability is 25, 25, 25, 25. State vector is also uniform. After measurement, I apply one measurement, it will be collapsed. State vector is collapsed, not a probability. Finally, you see the probability, all are equal. State vector is collapsed. The quantum state is collapsed, not a probability. The probability is also varying. That creates a randomness. C naught. 0, flip into a 1. That is get 1. That plus is nothing but say not gate. That not gate is working to change the phase 0 into 1. Controlled operation. Normal C naught gate. Act with the plus gate. First one is 0, so it will not work on. Whenever the first state is 1 means it will be flipped. Another state is also flipped. This is the entanglement. Entanglement happen whenever adding with the C naught with the H. Interference, why interference is working and how it is working on ISHU. How the real, anyway, you are working in your laptop only. Your laptop, you are making one program. That program is sent to the quantum computer. That quantum computer, whenever you use the commands like a quantum gate, it will be sent through the submitted job. The job is under a queue. That quantum circuit transmitted in the microwave pulse, it goes to the real quantum hard computer. That computer is worked on this. These are all worked on low temperature only. So you need to identify that. How to design a quantum computer. These things you need to remind. We are in the form of NISQ era, noisy intermediate scale quantum era. Intermediate means we are not below, we are not high. We are in the form of intermediate states. We are not in high and low. So that is, we are having that much intermediate level of qubit length. These are the applications that we can work with the quantum computers. Factor 3 into 5 is 15, that is easy. This number, what is the factor? That we are not able to know in our classical computer, it takes more years. So that quantum factoring is possible using the complex task. The faster processing is done in quantum factoring method. Using quantum computer, that is possible. Search your phone number, finding the owner name in a phone bill. That is also possible. Drug discovery, networks, post-quantum world. We are in the form of post-quantum world. Normal QFT. How the QFT 0, 1, ket plus and ket minus. How it transform. Hadamard case is a single qubit QFT, quantum Fourier transform. Added a 1, it will be show 0 and 1 only. 2 qubit QFT, I am encoded 1, 1, H, unitary operation, H, it will be shows superposition state. Finally, if you measure, you will get the same outcome. I need to run this. This is the way to run real quantum hardware. Finally, it will be run. What it is 0, 0. The outcome is 0, 0. 3 qubit QFT. Here I encoded 101. Finally, I get 101. The maximum probability only you need to know. Okay, these are all the steps. You need to add an inverse QFT. I am encoded 1, 1 here. This is a QFT combination, superposition with a rotation gate. This combination is a normal QFT. I added a high QFT. High QFT is inverse. If you add R is at pi by 2, you need to change the phase value. R is at minus pi by 2. It will be invert 1, 1. Finally, if you measure, you get again 1, 1 back. I run this in real quantum hardware. I'm using 101 here. I need to send this to real Sherbrooke hardware. I get 101 here. These are all the noise. Yeah. Okay. This is a simple applications. Any doubts in that?
Are we done, sir?
Thank you so much.
Thank you very much, sir, for this insightful talk. But before doing anything, we would like to address some questions from the participants.
Yes.
So the first question comes from Arnav, and he asks, what does it mean for a qubit to be in superposition after the Hadamard gate?
It will be 0 and 1 only. For example, after applying the Hadamard gate, it will be the state will 0 into the form of ket plus and ket minus. That is a superposition. Intermediate layer that up state is a 0, low state is a 1 means the intermediate way is a superposition. Here that intermediate way is a plus and minus state. That creates a superposition here. And the next question is, why do we use wave function or wave equation to represent the qubits, right?
Yes.
That wave function, all the wave functions are represented in the form of ket 0 and ket 1 only. That ket 0 and ket 1 is nothing but a qubits. Here, the superposition adding of ket 0 and ket 1 is a qubit representation. That is the wave function here. This one you get it.
If anyone has any further questions, you may unmute yourself and ask. There is another question from Aroha. Can you explain why entanglement does not violate general or special relativity?
Right?
Can you explain why
Yes.
entanglement does not violate general or special relativity?
Special relativity is rely on only the classical outcomes that these are all will be working only in the form of a normal relativity. Relativity is working only the basics only, right? In this relativity is also other principles, not in a quantum. That is, in quantum, determinacy will be there. Determinism is not at all there. Uncertainty principle is there so that the information can be sent. Information cannot travel faster than light. Yes, absolutely correct. It will state not violate the principles of special relativity because all are rely on that minus one. Hello.
So
Hello.
what,
Questions?
okay, I do have a question. What are the mathematical prerequisites one will need to have to get into quantum computing as a beginner?
Because all are in the form of vector state, right? Vector in the form of Hilbert space. We need to identify all in the form of matrix, right? So that we need a mathematics, linear algebra needed. Then only we are able to encode our gates in the form of matrix. All. In photonic also, if you are going, you need to add in the form of vector space. All are in vector, complex vector space. Qubits are all in the vector state, not in the classical states, right? In logical classical computer, gates are working on the Boolean algebra. In quantum, gates are working on the linear algebra. That linear algebra needed a vector space, right? Any doubt? Any other doubt?
We do have a quantum mechanics course in the fourth year of our BSc program. So I'm not certain. So would that be enough, or I mean, you might not have information about the course.
Quantum mechanics is enough, but you need to study about quantum mechanics is only the properties of quantum computing. You need to work on quantum computing. You need to know about what is the Python program and linear algebra, these things. If you want to start within a short duration of time, you work with IBM Quantum Learning. IBM has a beautiful structured course of IBM Quantum Platform. In that platform, you can able to access within 1 month. That 1 month, you can study about what IBM Quizkit open YouTube link also there. You can search in a YouTube IBM Quizkit channel. You can see the videos also. All are how to do the quantum gate simulation and quantum circuit making. If you know about the quantum gates and circuits and basics of quantum mechanics and some basics of understanding the mathematics involved, that you can be able to work on. What exactly quantum gates? Is it possible to design our own custom gates? Yes, you can able to make in IBM Quantum Composer also. Even if you want to add two gates, you can add that gate also. You can able to add that specific operation also you can work on. For example, if you want to change any rotation gates, you need to add pi by 2 is normally there. You can able to add with another pi by 180. But if you introduce any pi by 4 or pi by 6, if you add, you can design your own custom gate, but you need to tell what application that your custom gate is going to work on, how did you design your own new custom gate, how this that is useful than previously existing. That thing you need to know. Any other?
I believe that it is good night. Any further questions? Okay. Thank you so much, sir, for today. We are deeply grateful for your talk, and it was really inspiring. I myself learned tons, although some things went over my head. That's, but it was really insightful and informative. And I would like to thank all of you for being here today.